This experiment is about water quality and how various bodies of water can become acidic due to pollutants in the air. And this is kind of to consider the environmental impacts of manufacturing processes and such. But first, I want to go into a little bit of discussion about water quality and what all is in water samples that you may collect from different sources. And particularly natural bodies of water would apply to some of this discussion. Because a lot of our drinking water and so on is taken from sort of more natural environmental sources of water. There are a lot of things that need to occur in order to get this water to be purified enough for drinking and such. But, when you pull water from something like a river, as shown in this image to the left, you'll have particles present in there that would need to be filtered out by some sort of physical filtration mechanism. Some of this would be like silt and minerals from the actual soil surrounding the river, but some of this would also be due to biomass like algae and various bacterial presence and things like that may partially be able to be physically filtered out, but then you may also have some biomass that's too small for that kind of physical filtration. And the approach typically used for getting rid of the smaller ones would be to just kill them off with some form of sanitizer. A lot of times it would be something like bleach used, chlorine used to kill these smaller biomass bacteria particle presence. But even beyond that, you would have ions which are definitely too small to be removed by some sort of physical mechanism. So you have to start to apply more chemical mechanisms to remove these species. So there are specialty filters like activated carbon is good for removing things like chlorine. And you would also have cationic filters and anionic filters that are able to selectively bind certain ions so that the water can pass through, but the ions would not. These may or may not be used in drinking water applications, but there are other types of filtration applications where you want your water to be extra pure. You might bring in those type of filters. Some other things that are dissolved in the water are various gases, and we are going to focus on gases being dissolved in the water, but this also is related to the pH of the water. Because a lot of gases, when they dissolve in water, form acidic species. And so we will focus on the idea of the pH of the water source and the gases involved. And so just a bit of explanation as to why the dissolved gases cause a decrease in pH. We can look at sulfur dioxide as a gaseous pollutant. When it is added to liquid water, it dissolves and forms a sulfurous acid species, which is shown here. But that sulfurous acid species, with one of its protons removed, makes a H3O plus molecule in the water solution. So it may be better to write it as H2SO3, which then dissociates into the water to make H3O plus and HSO3 minus. Very similarly, nitrogen dioxide is a gas, and when it dissolves in water, it'll make nitric acid and nitrogen monoxide, and the nitric acid then dissociates into H3O plus and NO3 minus. So I have the H3O plus ions highlighted in red because these are the species actually contributing to the acidity. So when H3O plus is generated, that causes the concentration of H3O plus to be higher. Therefore, pH is a lower value because it is a negative log value. All right, so when you have a combination of sulfur dioxide and nitrogen dioxide, you get even further range of species that could be present. So if both gases are in the same vicinity, you would get some nitrogen monoxide and some sulfur trioxide gas. And the sulfur trioxide gas dissolves and makes essentially sulfuric acid, H2SO4, which dissociates into H3O plus and HSO4 minus. The big hot topic gas that we all hear about, contributing to a lot of environmental problems, is carbon dioxide. Carbon dioxide also forms acidic species when it is dissolved in water. It forms carbonic acid, H2CO3, which then dissociates into hydronium and HCO3 minus, which is a bicarbonate ion. All right, so all of that could be happening based on what types of pollutant gases are present. And an application that explains why this is a problem environmentally would be to look at species that make their structures in the ocean out of calcium carbonate. And so corals are a perfect example, but there may also be other marine life that use calcium carbonate or limestone as part of their structural material. But coral, essentially the hard structural support, is made up out of limestone or calcium carbonate. So we're going to investigate how we can figure out the acidity of a unknown acid sample by reacting it with calcium carbonate to kind of simulate what an acidic ocean water would do to a coral species over time. And we will investigate this by pH. So we'll look at, we'll have kind of this receiving flask down below. I'm calling this in the figure the post-reaction solution, because anything that passes through the column is landing into our collection flask. As we're passing acid through the calcium carbonate, it should react and neutralize with the calcium carbonate, so the water that falls through would be neutral pH or something close to neutral pH until all of the calcium carbonate has reacted. Then any excess acid that comes through should show us a sharp change in our pH, indicating that we have exactly reacted all of our calcium carbonate. This is pretty similar to the idea of a titration, just a different type of apparatus, but we will have measured the mass of the calcium carbonate that we're putting into our Pasteur pipettes. We will not know the concentration or the identity of the acid to kind of simulate that in samples of ocean water. It could be a mixture of different acids present, but we'll use the stoichiometry of this reaction between H3O plus and calcium carbonate to help us determine what the concentration of H3O plus must have been in the original acid by detecting the point at which all the calcium carbonate has reacted. You can find that reaction in the protocol as well, so you can see what the stoichiometric relationship is and what products are generated. But to construct your Pasteur pipette, you'll just have a little piece of cotton in the bottom of the glass pipette. You'll use whey paper like a funnel to carefully put in your weighed out calcium carbonate on top of the cotton, and then you'll inject aliquots or small portions of your unknown acid in there and allow it to drip through. I've found that it drips through very slowly, and that actually using a pipette bulb on the top of this to kind of force some of the liquid through slowly is helpful. You just can't do it too quickly or it won't have time to react with the calcium carbonate, and you'll get inaccurate measurements of changes in pH. All right. A final kind of aspect I wanted to discuss for this experiment is that you'll be measuring a few different things for various water samples, so you can start to think about what these measurements mean, but you'll measure the conductivity of water solutions, and you'll also measure the pH of water solutions. And the kind of last thing we'll talk about in a moment is the tests you'll conduct to find which dissolved gas species are present. But there's also a part of the experiment that you will specifically investigate the relationship between conductivity and pH. And your group is going to have to come up with a procedure because you may have a specific variable that you wish to investigate, such as how the concentration of a particular species would affect both conductivity and pH, how the acidity of an acid would affect both of these. Maybe you would want to look at how the type of compound involved would affect conductivity and pH. There's a bit of openness here to determine what type of research question you want to answer, but the key is to try to unravel whether conductivity and pH are always directly related or if there are other factors that come into play. Okay. So when testing for dissolved species in your original water samples in the beginning of the experiment, we have two strategies specifically for detecting the presence of nitrogen dioxide and sulfur dioxide. So when you want to detect nitrogen dioxide, you'll combine it with an iodide source because nitrogen dioxide can oxidize your iodide ions into iodine, the molecule, and this is the product of the nitrogen dioxide gas in this reaction. But the reason this is going to allow us to detect nitrogen dioxide presence is that once your I2 forms, if you have starch present in the solution, you make a dark I2 starch complex, just like we saw in the kinetics of the iodine clock reaction. So when your solution turns dark brown, even if it's like really faint, that will tell you that there is some nitrogen dioxide present in the water sample. If SO2 or SO3 were present in the solution, we can detect them using barium ions because barium is able to create a solid precipitate with sulfate ions that are present in solution. So SO3 we know already makes sulfate ions essentially when it is dissolved in water, but SO2 we need to manipulate a little bit to force it to become SO3 so that it will go through and make sulfate ions that can allow that precipitate to form. So the first thing would be to just add some hydrogen peroxide to your solution. If there is any SO2 present, it will react with the hydrogen peroxide and create SO3. So that's an oxidation step. And then the SO3, because there's water around, will generate SO42-, which can then combine with barium to give us that solid white precipitate. So if you see the solution become at all cloudy or any solid particles falling to the bottom of the test tube or whatever you're reacting in, then I would say that that indicates that one of these two, or maybe both, were present in the sample, and you would record that in your observations for the experiment.